Okay, well, thanks for the lovely introduction, Colleen, and thank you all for coming to listen to me talk about the geology of central Chile's long-lived volcanic arc. So today I want to share some of the more significant results from my PhD work at Santa Barbara. But before I dive into that, I'd like to start with my acknowledgements. So first and foremost, I thank my advisors, Phil Gans and Andy Weiss, who you can see here living the good life in the field in Chile. I'd like to thank both of my field assistants. I had two amazing field assistants, Tim Gross and Ryan Thress, and they're both pursuing graduate studies of their own now. I'd like to thank John Cottle, Gareth Seward, and Andrew Kylander Clark for technical support at UC Santa Barbara, mostly on the geochronology front. And I owe a debt of gratitude to the Earth Science Department. They supported me in all sorts of ways through TA-ships, RA-ships, internal scholarships and grants. And I also thank the AAPG and the GSA foundations for funding a couple of my grant proposals that supported this work. Okay, so I thought I'd start with a statement of my motivation for my PhD research. So what you're looking at here is a very schematic diagram of the Andean type subduction margin. So a lot of you are probably familiar with this diagram, but I'll explain it anyway. So basically what you have is oceanic crust subducting beneath continental crust and continental lithosphere. And these subduction margins are arguably one of the most important features on planet Earth, in that they're a site of major chemical exchange between the Earth's mantle and the Earth's surface. So, basically what you have happening is this oceanic lithosphere is subducted down into the mantle. It's melted and reabsorbed into the mantle. And on its way down, it also initiates melting of the overriding upper mantle, and these melts rise to the surface and erupt in volcanic arcs, which help build continental crust. So tectonically, they're very, very important. From an economic standpoint, they're also really important in that these volcanic arcs host some of the world's biggest ore deposits. You hear a lot about these copper porphyry deposits in particular in South America. And they also serve as the backstop to fold thrust belts that often bear petroleum. From a geohazard standpoint, they're also really, really important. One is that they produce the largest earthquakes or strongest earthquakes in the Earth. And actually in Chile, and Mike, you can correct me if I'm wrong here, but I think the strongest earthquake ever recorded was in Chile, and I think it was a 9.5 magnitude. And then more recently, in 2010, there was the 8.8 magnitude earthquake, which actually canceled one of my field seasons, unfortunately. Okay, so obviously these earthquakes impose a huge geohazard, and then also, some of these eruptions, these volcanic eruptions, can be quite violent and also pose a threat to civilization. Okay, so despite their importance, we don't really have a good understanding of their long-term evolution, the long-term evolution of these subduction margins and associated volcanic arcs. And when I say long-term, I'm talking tens of millions of years. And so you might ask yourself, well, why is that? Well, if you think about extinct volcanic belts, such as my personal favorite, the Sierras in California. This is the Eastern Sierra that you're looking at here. Mount Whitney's maybe somewhere up there. And for those of you who've spent some time traipsing around in the Sierras, you know that you see a lot of granite, right? And so the granite it doesn't really tell you a whole lot about what was going on when the volcanic arc was active, right? So the granite, is basically the fossilized magmatic system of these of this volcanic arc, and this granite's been exhumed, brought to the surface, and all the supracrustal sequences, the volcanic sequences recording intra-arc geodynamics, have long since been eroded away. So it doesn't really give you much information. If you go to the opposite end of the spectrum and think about active volcanic arcs, such as this active volcano in Central America, whose name I forget off the top of my head. You think about these systems, a lot of times the older volcanic sequences are covered by expansive, young volcanic deposits. And in this case, covered in jungle, and maybe if you're in a colder climate, they might be covered by glaciers and snow. So the take-home point is, wow, do you guys hear that noise? I hear some feedback there from the microphone, maybe. Gone now. Okay. So again, if you think about these younger systems, you don't really get a good look at or deep incision and a good look at older volcanic strata recording these geodynamic processes. So it really takes a good coincidence of relatively young uplift and deep incision and an arid climate to get a good look at volcanic, a good long look at volcanic strata recording geodynamic processes over a long time period. And it turns out we have such one of these coincidences in central Chile. So here's a photograph of my field area. You're looking at what we call the Abanico Formation in central Chile. So this is in the Tinguiririca River Valley. And it's just, so what you're looking at is almost 3 kilometers of section just in this photo. So all these stripes are volcanic and volcaniclastic deposits. They're all kind of apparently dipping off to photo right there. And beautifully exposed. And to our surprise, based on previous reports, this section that you're looking at here actually represents a pretty large interval of time, approaching over 60 million years. So this area affords an excellent opportunity to study arc processes over a really long time frame, or at least in the time scales I work. Okay, so some of the overarching research objectives of my research was fundamentally to investigate long-term continental arc processes. And again, when I say long-term, I'm talking tens of millions of years. And at the same time, I was trying to decipher the local tectonic and magmatic history of central Chile's Principal Cordillera. So specifically, I was trying to address some of these questions. What are some of the patterns of magmatism in this area? Was it continuous or episodic over these long time intervals? And are there any discernible trends, compositional trends that we can track in that record? Did these arc strata accumulate in a tectonic basin or a quiescent platform? And is there any sort of detectable deformation? And if so, what's the timing and style of that deformation? Now, I didn't fully answer all of these questions, but I think I made some strides at understanding long-term arc geodynamics. Okay, so here's the talk outline. I'm going to start off by just giving you a brief geologic setting of central Chile, and I'm going to give you a whole slew of results, including geochronology, show you my mapping, the stratigraphy I put together for this area, a little bit about structure, then I'll end with a preliminary tectonic model for this region. Okay, so starting with the geologic setting. Well, first, the tectonic setting. So this is a simplified tectonic map overlaid on a shaded DEM of southern South America. And it's a pretty straightforward setting. So currently you have the Nazca Plate subducting beneath the margin of South America at a rate of about 80 millimeters a year. And associated with that subduction zone, you have a volcanic arc. So all these little red triangles you can see here, those are the active or Holocene volcanoes associated with that subduction zone. One of the first things that pops out at you when you look at this is that there's a noticeable gap in the volcanic arc right here. And spatially, that coincides with the region of what we call flat slab subduction. So these lines you can see here, those are contours to the depth of the downgoing plate. And you can see that it flattens out in this region, and thus you have a gap in magmatism there. My field area is shown by this orange star right here, my area of study. and it's in the northern end of what we call the southern volcanic zone in this part of the world. And it's actually an interesting location where it falls in this transition zone between normal subduction and flat slab subduction. Okay, so that's what the tectonic framework looks like today, but people think that it actually hasn't changed much since the early Jurassic. So people think subduction beneath the South American margin has been fairly continuous from the early Jurassic to the present. So it's a really, really long-lived subduction zone. Okay, so zooming in a little bit closer to my field area, my focus of study, you can see by this little box right here. This is, again, another shaded DEM of South America's western margin at this latitude. And classically, this region is divided into 4 or 5 what they call morphostructural zones. So I'm going to walk you through this, starting with the coastal Cordillera along the coast here. This is a low elevation mountain belt, really similar to the coastal ranges in California. And then as you come eastward, you get into the Central Depression. This is where you have a lot of agriculture and vineyards and things like that. And then as you continue eastward, you get into the Andean main range, which you can see here. And first you get into the Principal Cordillera, which is where I was working. And then you cross the Continental Divide and go into Argentina, and you go across the Malargate Fold and Thrust Belt, and you drop in elevation as you go down to the modern foreland. Okay? So these are some elevation profiles corresponding to this swath in this long rectangular box I've drawn there. And all I really want to show with this is that, well, first off, the red line is the maximum elevation, the green's the minimum mean elevation, and then the blue's the minimum elevation. So I've marked roughly the spot of my study area, and if you compare the max and min, you can see there's quite a bit of relief there, well over 2 kilometers. And this is kind of a blessing and a curse. It's a blessing in that we have deep incision of the bedrock there, so we get a good look at the geology. But it's also a curse when you try navigating and hiking around on this stuff, as real challenging, as I'll show you in some upcoming slides. Okay, so each one of these morphostructural zones is accompanied by changes in the geology. So this is the same area, but I've overlaid a general geologic map I stitched together. And you basically have 4 main belts of rock. So again, starting in the west, in the coastal Cordillera, this green unit you can see, these are mainly Paleozoic basement and intrusive rocks. As you go into the eastern coastal Cordillera, these blue units you can see here, these are Mesozoic, volcanic, and intrusive sequences, and people think they represent what would have been the early Mesozoic arc. So this would have been the location of the early arc as it initiated. As you go into the Central Valley, it's mostly covered by Quaternary sediments and volcanic deposits. And then as you start to get into the Andean main range, this brown unit you can see, this is what we call the Abanico Formation, and it consists of these really thick sequences of volcanic and volcaniclastic deposits. And again, this was kind of the focus of my study. And then as you march even further eastward, you get into these Mesozoic sedimentary, mostly dominantly sedimentary sequences, but there are some volcanic units in there, and they're highly deformed. It's the fold thrust belt. I've highlighted or bolded some of the larger faults with these dark squiggly lines you can see here. And then as you continue into the modern foreland, the foreland's covered by young Quaternary sediments. Now, the modern arc, kind of more or less, at least in this region, it kind of follows the Chile-Argentina border. You can see these red triangles are some of the active volcanoes now, and there's some young volcanic deposits associated with those that you can see in yellow. Okay, so one take-home point from this is that it appears that the position of the volcanic arc is marched eastward since the early Mesozoic. So it was at one point here, and now it's over here. Okay, so a little bit about the general stratigraphy of my field area. It's pretty straightforward. So And again, this is for the Principal Cordillera between about 33 and 36 degrees latitude. And basically what you have are these Jurassic through Cretaceous, marine and continental sequences, presumably overlying metamorphic basement. And classically, people have in turn interpreted these sequences to have been deposited in a retroarc or a back arc setting, so behind the arc, east of the arc. And then this sequence is unconformably overlain by this thick succession of the Abanico Formation, so it's a thick succession of these volcanic and volcaniclastic deposits. And then, to me, it seems kind of arbitrary, but people break out this other formation, the Ferriones Formation. I actually haven't seen it myself, but based on descriptions, it sounds almost identical to the Abanico Formation. I think it might be somewhat arbitrary sometimes the way people break that out, especially considering there hasn't been a whole lot of geochronology data from this area presented. So people interpret these deposits as being intra-arc deposits, and that these intra-arc deposits start off accumulating in these regional extensional basins. So you had crustal extension, the crust is being pulled apart, and that was essentially accommodating these thick successions of intra-arc deposits. So that's kind of a classical interpretation and the kind of the prevailing model for this region at the moment. So people kind of discuss this depositional hiatus through the late Cretaceous through a good part of the Eocene, and as I'll show you today, I have a lot of reason to suspect that there wasn't a depositional hiatus here, and in fact you were accumulating arc strata, and I'll talk more about that in a minute. Okay, so stepping out just a little bit, here this is another simplified geologic map just showing the Abanico Formation, the Ferriones Formation, and their equivalents. Notice that we're spanning quite a bit of a latitude here. We're going from, I don't know, 33 to over 38 degrees latitude. And the first thing I want to say is that even though geographically these deposits are really widespread and they're really thick, there really hasn't been a whole lot of work done on them. You know, if this was in the United States, these things would probably be picked over pretty good. But as far as I can tell, there's only been a handful of studies, or careful, detailed studies in the modern literature. Now, if you kind of dig deeper into the South American literature, you'll find some stuff, but it's usually generally not that helpful. And for one, it's not in English, which it's kind of hard for me sometimes. But just not readily available and just really not out there for people to consume. So some of the detailed studies that are in the literature kind of give conflicting reports, and part of that just might be that we're spanning a lot of degrees of latitude here, and it's almost ridiculous to be making these correlations over such great distances, but people do anyway, and they get in fights about what they're seeing or reporting. The main things I just want to point out in this diagram is that concerning the onset of magmatism as recorded by the Abanico Formation and its equivalents, there seems to be some discrepancies between reports and a long latitude here, long strike of the Principal Cordillera. So the gray boxes are just showing the timing of magmatism as recorded by the Abanico Formation, and you can see that some people have it, beginning in the Eocene, where others have it starting in the Oligocene or late Oligocene, almost Miocene. And then the gray boxes are showing the timing of contractional deformation or shortening and inversion or I guess shortening deformation of these deposits. And again, you can see that there's some discrepancies here, and it's not apparent if this is just erroneous interpretations of the geology or if these are actually real. What we really need are a lot more detailed studies, and that's where I was trying to make a contribution with my work. Another thing people like to do is they take their observations, their local observations, and they try to tie it to this pretty well-constrained convergence history for this region. So people look at this spike in convergence rate around the Oligocene, and so depending on which study you belong to, some people will be like, well, this increase in convergence rate, this tripling in convergence rate corresponds to the onset of crustal extension and accumulation of these thick sequences, whereas other people, say, well, actually, that corresponds better to times when shortening was starting to happen. So my feeling is that, well, first off, we need a lot more detailed studies before we can even begin to make those type of arguments, and I don't really think, I think a lot of other things should be considered other than the convergence rate alone. Okay, So just to kind of summarize the prevailing tectonic model for my field area, is beginning in the Mesozoic, it's basically a three-part model. So, you know, people look at those Mesozoic sequences, those marine and continental sequences, and they interpret those to be deposited in a back arc setting. And then in the Eomiocene, people think the arc front migrated to the Principal Cordillera during this time, and that's when we got deposition or accumulation of strata making up the Abanico Formation. And then those, and people tend to, the classical interpretation is that, again, we had these extensional basins that were accumulating all that strata, and then those basins were inverted during the Miocene, during shortening and uplift of the Andes. So that's the prevailing model right now as it stands. And today I'll show you that there's reason to believe we should maybe rethink this model or definitely revise it. Okay, so into some of my results, starting with the geochronology. And I want to talk about the geochronology first because it's really is in some ways, besides my map, kind of the foundation of my study here. It kind of allows me to say some pretty powerful things about the geology here. Okay, so a little bit about previous work on the geochronology front. There really wasn't much, okay? There were a couple of potassium argon ages floating out there, but those were a bit suspect. And it wasn't until 1996 where we kind of got our first good, somewhat reliable argon-argon age. And this was actually work done with my co-advisor, Andy. And this age was actually from my map area. And so they dated some strata around 36.22. And for this region where I'm working, this remains the only reliable age, and thus the oldest age reported for the Abanico Formation. And people have used this as kind of the lower limit for the Abanico Formation. So people currently think the Abanico Formation can't be much older than 36.22, and I'll talk more about this in a minute. So why aren't there that many ages out there? You know, the potassium argon and argon-argon techniques have been around for a long time, and I think part of the reason is that these rocks there tends to be this somewhat pervasive metamorphism in the rocks. So this is just kind of a chart summarizing some of my observations by others, and you can see that we have a lot of these kind of lower grade metamorphic minerals trending in some cases up to green schist facies. So anyone who's done any argon-argon dating knows that when you start to get into green schist facies, you're kind of hosed as far as dating volcanic intervals. And so I think this is largely why there's just not a whole lot of geochronology data out there on the Abanico Formation. Okay, but spending a lot of time out there, and Phil actually started working there long before I did, my advisor. You know, he found that, okay, there's this kind of this pervasive metamorphic conditions here, but if you poke around long enough, you can find some fresh intervals, and we did have some success both using the argon-argon technique. Okay, so lucky for me, I went to UC Santa Barbara, and I'm lucky for a number of reasons, one being the geographic location. So for those of you who haven't been to the campus, this is the campus you're looking at right here. It's right on the ocean. There's actually a really good surf break here where I cut my surfing teeth. And anyway, just right down from my office, a couple buildings down, I had some really world-class instrumentation to utilize, and I got great internal rates using it. And in particular, my advisor, Phil, he runs the argon-argon lab in Santa Barbara. So that was kind of an unlimited resource for me, which is good because I was working on metavolcanic rocks, so I could, you know, I didn't have to be too choosy about my samples. And then when I showed up, they just finished construction of the LA ICP-MS facility. Okay, so this is a laser ablation ICP-MS facility that you can use for dating zircons. It's a world-class, really, really nice facility. So those are the two techniques I utilized, and here's some pictures of what the labs look like. So this is the gas extraction line and mass spec in the argon lab. And then this is the multi-collector and the LAICP-MS lab that you can see here. And as a fun little side note, you can see the laser ablation system here. That's actually from Photon Machines down the road in Bozeman. And then there's a single collector, atom collector back here. They have a split stream set up. And if you guys were here for Julia Baldwin's talk, this is the same lab she does all her dating at. And Anyway. Okay, so I ended up with a whole smattering of new ages. This is a generalized geologic map of my focus area. So the brown unit, that's the Abanico Formation. And I did some reconnaissance work and mapping in the Azufre drainage, but most of my work was focused in the Tinguiririca drainage here. And you can see that I have pretty good spatial distribution of my ages, and it turns out a pretty good temporal distribution as well. At the end of the day, I ended up with about 19 unique argon ages, 30 ages total, but 30 ages for 19 samples, and about 23 uranium lead zircon ages. So for those of you who aren't familiar with this type of work, this is a whole lot of data for this type of study, especially for such a small area. Typically when you see a paper, they might have 6 ages or so. So I feel really confident about how old these rocks are. Okay, I'm not going to show you every last single piece of my data because that'd be boring for all of us, I think. But here's some examples of what the argon data looked like. So this is a young, moderate, and old age here. I would like you to focus on. I'm still hearing that feedback. I'd like you to focus on these top 3 boxes here, and I don't really have time to go into this, but basically what you're looking for is you want your age, what we call an age spectrum, to be flat for these type of analyses, and you can see they're fairly flat, and I'd say they're actually really good data for metavolcanic rocks. So that's kind of typically gives you a flavor of what the argon data looked like. And then here's what the uranium lead zircon data looked like. Again, these are representative young, moderate, and old ages that I obtained. These are cathodoluminescence images showing some examples of what the zircons looked like for each of these samples. So I tried to date at least 35 grains per sample. I'm not sure if you can see that on the screen, but you have these nice little tree rings in the simple structure. It's what we call oscillatory zoning, and that's what you want for igneous zircon. And again, for those of you who are here for Julia Baldwin's talk, she showed you a lot of these what we call Tara-Wasserberg plots. So it's one way to look at uranium lead data. And I'm not going to go into the details of this. You want to know more about it, see me after the talk. But basically, for each analysis, so these are circles. Each one of these circles is an analysis on a single grain, and it's just showing you error in X and Y, and instead of error bars, it's a circle. And there's this, what we call a concordia line, this blue line here, and ideally you want all your samples, all your analyses to be sitting on that line. And you can see that not all of mine do, especially for this young sample. They're kind of drifting up and to the left here, and that's okay. This is a common problem for igneous rocks. It's called common lead, and we can correct for it, and it's actually a pretty typical thing you see for igneous zircon. But these are what we call really good, or excellent data. Okay, so this is bringing all the data together and sorting it by age. So the argon data is shown by these red points here, and then uranium lead data is shown by the blue points. So I simply just sorted these by age, and there's a couple of things I want to point out to you on this plot. First off, and I promise there's some field photographs coming, so don't leave yet. First off, there's I want to point out that there's this, I drew in this line here, and that's the oldest and the only age reported, reliable age reported for the Abanico Formation. And so you can see that I have a lot of ages that are quite a bit older than that, so I'm getting down to the late Cretaceous here. Okay, so that was pretty surprising to us. It's a pretty significant result. It's just, I just sorted these by age, so it's a sample. I could have labeled each individual sample, but it gets pretty crowded. So, so anyway, so I have a lot of these old ages, so that's a pretty significant result in itself there. And then when you look at these, they seem to be a bit clustered, right? And I plotted this histogram of, by age, and you can see that there's some clustering of the data here. Now this could be a number of things. One thing it could be is just sampling bias, right? Maybe I was sampling the same intervals throughout my map area, and those just tend to work out better for geochronology. So that could be one explanation. Another explanation is maybe we had, episodes of volcanism delineated by periods of emergence and erosion or quiescence in general. So maybe what we're actually seeing here is post-volcanism through time. I can't really make a strong argument for that now, but what I'd really like to do is keep working in this area to the north and south and collect more of this data and see if this trend continues. It's definitely something to think about, and I think this provides a really robust data set for future researchers to build upon. Okay, another interesting little tidbit about this data is that I dated a number of samples by both techniques. And for those of you who aren't familiar with uranium lead zircon geochronology, one major concern that we're always worried about is, especially when you're trying to date a volcanic rock and get a proxy to the eruption age, you're worried if these zircons floating around are inherited or xenocristic in origin. Zircon is a really tough little bugger. It has a really high melting temperature or crystallization temperature, which makes it really great because when you're working in metavolcanic rocks like myself, we want a geochronometer that's really tough. And so it's good, but it's also bad in that it can get recycled, or it can be, if you have magma ascending, magma can pick up xenocristic zircon. At the surface, if you're dating a tuff, you can have detrital, or they can pick up zircons at the surface. So it's something to really worry about. It's a big concern to geochronologists. And what I was able to basically prove with my data is that, no, I don't think these are necessarily xenocrysts or inherited grains. So each one of these dots is a sample I dated by both techniques. So I have the argon-argon age on the y-axis and the uranium-lead-zircon age on the x-axis. And if they're in agreement, you should get a slope that's roughly 1, right? And I'd say that they're in pretty close agreement. There's a couple up here where the argon-argon data was a little suspect, not a perfectly flat spectrum, but more or less they're in pretty good agreement. So I feel pretty good about using these zircon ages as a rough proxy for the eruption age, some of these lava flows. Okay, so coming back to this chronostratigraphic chart I showed you guys earlier, you remember there was this depositional hiatus from the Paleocene to the Eocene? Well, if you remember, I'm getting ages as old as 74 MA and all the way through this time period and up into the Miocene. So I'd argue that no, there's not this depositional hiatus, and my results pushed back the lower, or pushed down the lower boundary of the Abanico Formation to at least 72. And I never actually saw the stratigraphic base of the Abanico Formation, and I'll talk more about that in a minute. But conceivably the Abanico Formation could be much older than this. So this is a major result, and it has major tectonic implications in that okay, well, if we're going to interpret these deposits as intra-arc deposits, which I'm fine with, and I'll talk more about that in a minute, that means that maybe the arc front had shifted eastward or expanded to the Principal Cordillera, from the coastal Cordillera to the Principal Cordillera by the late Cretaceous. So that's some tectonic implications, and when I finally get this stuff published, I think it's going to ruffle some people's feathers, but that's why science is fun. Okay, so let's give this a little bit of context. I want to talk a little bit about the mapping. So I can't start without the previous work, and this is just too good. I have to put this in every talk I give about this stuff. So some of the pioneering work in my field area was done by Charles Darwin on his maiden voyage there, and he did some traverses across the Andes really close to my field area, about 100 miles north, but really similar geology. And he was the first one to describe the Abanico Formation. He called it the Porphyritica Formation based on all the porphyritic textures and all the lava flows that he was seeing. And you can get all this stuff online, and it's amazing. His descriptions are much better than mine would ever be. It's a really amazing guy. And so anyway, he crossed the Andes in 2 places, and he did a little bit of mapping, and he put together these cross sections, which are amazingly, they're pretty good considering he was only there for like a couple of weeks. He also looked at the Mesozoic sediments there and correctly identified Cretaceous fossils, so he was able to assign a Cretaceous age of that, and by association, he noticed that the Abanico Formation was overlying these Cretaceous sediments, and so he assigned a late Cretaceous age to the Abanico Formation, which turns out was probably right to begin with. Okay, so after Darwin, there wasn't really a whole lot of work done until 1960, as far as I can tell, and a person named Clone went into this region and did some really coarse reconnaissance-style mapping. So this is kind of zooming in on my field area here a little bit. And yeah, he mapped the Abanico Formation as these green units here. But interestingly, he also mapped the Farallones Formation as this yellow unit that no one else has mapped since him. Anyway, he kind of followed suit with Darwin and assigned a Cretaceous age to the Abanico Formation in this region. And then after Clone, as far as I can tell, there wasn't really much mapping done until my advisor, one of my co-advisors, headed here for vacation. So my co-advisor, Andy Weiss, is a paleontologist. He mostly focuses on mammal fossils. And he was working, for his graduate work, he was down working in, or maybe it was his postdoc work, he was down in Patagonia, and he'd heard about these hot springs up by Santiago, Termas del Flaco. And the Termas del Flaco is also famous for this trace fossils. So it has these dinosaur tracks, a sauropod. It's interpreted to be sauropod trace fossils. So they were, they wanted to come see these, and they wanted to sit in the hot spring. And I don't know if they had too many beers or sat in the hot spring too long, but they got totally lost and went up the wrong side of the drainage and ended up on this pass, and then started coming down this way, and they started seeing these baseball-sized nodules. And being a paleontologist, he knows that if you crack those open, a lot of times you find fossils in them. And so he did just that, and he saw this jaw. Well, he's a mammal paleontologist, and he knew right away that this is a mammal fossil. And he'd looked at the geology map, Clone's map, before he went here, and he thought these were all supposed to be Cretaceous and older units. So right away he was, okay, what's going on here? So he decided to pair up with his Chilean colleague, Ronaldo Cherrier, and they did some geochronology. This is that age I showed you earlier. They did some really rudimentary mapping and decided that the Abanico Formation was no older than Eocene. It was maybe Eomiocene in age. Okay, so that's all that's been really done, and ever since then, Andy had a suspicion that, based on fossil evidence, that maybe they were wrong on this original report, and that maybe some of these intervals are a bit older, and he was really waiting for the right person to go down there and map it, and I guess it was me for some reason. Okay, so we'll talk a little bit about my geologic mapping strategy. So I did all my mapping at 1 to 10,000 scale, and I really lucked out because right when I started grad school at UC Santa Barbara, they updated all the Google imagery for this area, and it's just like it's really sharp, really good. I mean, you almost don't have to go there; you can just map right on the imagery, and that was a big help because all the topographic bases, I don't think there's one that I could find that was I think like 1 to 100,000 scale was probably the best I could do, which is really coarse and not ideal. So I did all my mapping at 1 to 10,000 scale on Google imagery, and I mapped about 180 square kilometers, so that's about equivalent to a 7.5-minute quad, which doesn't sound like much, but when you're mapping at 1 to 10,000 scale, that's quite a bit of mapping. It's a lot of panels. So I had my work cut out for me because not only was I trying to define and describe a mappable stratigraphy, I was also trying to work out some pretty complicated structure. And anyone who's worked with volcanic deposits know that they can be a nightmare because they're very discontinuous, and I really had my work cut out for me. So my strategy is I start off just kind of stepping back and looking at sections and being like, okay, what are the weathering characteristics I can see, color differences, and I got my boots on the ground and started describing things in detail, making detailed petrographic observations, both in the field and in thin section at the lab. And then I started looking for stratigraphic sequences that I could correlate through the map area, and the geochronology data was really key for this. I couldn't have done it without the geochronology, at least not with confidence. Okay, so when I interviewed here and I gave kind of a similar talk, I got some criticism that I didn't show enough field photos. So I'm going to try to make up for that now and maybe regain some of your interest for those of you who are falling asleep. So I thought I'd start with this picture, and you know, this picture I think does the best. It's the best picture I have as far as capturing the scale of this place and how intimidating it really is. And still, just even the photo doesn't quite do it justice. But we really had our work cut out for us. You know, there's a lot of cliffs, there's a lot of relief, and you know, trying to get up on these rocks and make detailed observations and collect samples, as imagined, was pretty challenging. You know, you stand at a vantage point like this, and you're like, oh yeah, I can just I'll just go right up this, no problem. And no, it's not that easy. And so mapping was really, really, really slow. It's not like Montana where you can basically walk anywhere you want, more or less. This place you really had to have a careful strategy. Another picture is kind of showing the scale and kind of showing some of the hazards. So this is a kind of a common situation we found ourselves in on a daily basis. So it's my colleague Dan here, and you can see he's kind of hanging on for dear life on this slope. And the reason is, like, these light purple patches you can see here, that's bedrock, and then the darker purple are these like marble-sized pieces of gravel. And then, you know, quite commonly you got a cliff underneath you. And so, you know, it's kind of hard to focus on the geology at times, maybe like 50% of the day. Became more of like I started asking myself, are we out here on an adventure expedition or something? Or are we actually doing geology? It was quite the experience. Yeah, and so sliding off of cliffs was a big hazard, but falling rocks were actually a really big hazard too. And there was a lot of tremors and earthquakes when we were there, and rocks would get dislodged and come down on us. And as an example, I took this as photo evidence for my advisor to show him that my PhD project was really a product of blood, sweat, and tears. Other dangers were tarantulas, and it's kind of funny. I have a funny story behind this photo. We were just down the first couple of nights, and we always slept under the stars because we actually, believe it or not, had problems with people getting into our camps and stealing stuff and rummaging through our stuff. So we didn't set up tents because we didn't. It's like a beacon, you know, saying, you know, come look in our camp. And anyway, one of my field assistants, he's from LA, kind of green at camping and stuff, and you know, he's like, I don't know about this. You know, I feel like a spider's gonna crawl on my face or something. And I was like, you're silly for even entertaining that thought. You know, I made fun of him. You know, I think we'd had a few beers at that point. And then lo and behold, of course, we wake up the next morning, and it's not by my head. It has to be by his head. There's this tarantula wandering around, and I never heard the end of that one. Saw a lot of condors. They'd circled us relentlessly, probably hoping that we'd die of thirst and starvation at some point. I saw a lot of Andean foxes. This little guy followed me around for a couple of days. Unfortunately, he was injured. I hope he survived. You know, other than that, we just saw a lot of livestock. Didn't really see a whole lot of other wildlife besides these parrots. I never got a good picture of it, but there's these migratory, colorful parrots that would come in and out for the season. We picked up some stray dogs, which was fun for a while. But unfortunately, the black tri you can see up here that we named J Boogie, he started having seizures when we were up high in the high country one day and slid off a cliff, plummeted to his death. And it was really sad, but I think it was a good wake-up call because we'd been getting a little too adventurous those past couple of weeks, and kind of brought us down a couple notches. Again, this is another scale photo. So this is looking over the Tinguiririca River Valley, and I just show you this photo just to show you how much walking we did. So I didn't have any form of transportation, which really wouldn't have been much help anyway. But you know, so Termas del Flaco would be photo left out here, and so we had to walk at least this distance every week to bring supplies in, and then pack rocks back out. But this is actually, that's probably only half to maybe a third. Like sometimes we're way down the valley where we had to come several miles all the way back up to Termas. And you know, sometimes we'd be along parts of the road, but surprisingly people wouldn't pick us up if we happened to see any cars. So we did a lot of walking. Not to mention every day we were marching up and down all these ridges. So this the Rio Tinguiririca was too swift to cross by foot or by horse for that matter, and there was only a couple of homemade swinging bridges, so we had to strategically plan where we wanted to cross the river when we were going out and coming back from the field. So this is my field assistant Tim trying to, this thing is scarier than it looks. It had really rocky. This is like a typical camp. There's not a whole lot of flat spots in this area. So you kind of make do, and we ended up a lot of times in these drainages. And for one, just getting into this drainage, coming up this really loose footing for a heavy pack, bringing in a week's worth of food. And then again, falling rocks are a big problem. And in fact, this particular camp, one day we're standing there in the morning having our morning coffee, and a big boulder dislodged and just rolled right by our camp. So I always slept with one eye open, although I wouldn't really be able to do much if a rock fell on me. And we didn't bring tents, but we brought tarps just in case the weather turned bad, and we'd have some makeshift shelters you can see here. We mostly camped on a backpacking stove. I found after about three months continuous use, 6 days a week, those things tend to break down. So sometimes we'd have to finish the field season cooking on fire, which was actually pretty stressful because there's not too much wood and stuff to burn there. So we had to really think carefully about that. Just a picture from camp. It looks ridiculous now, but this was actually pretty comfy. Lots of surfaces to sit on and put things on, a lot of little cubby holes to stash your food. It's pretty homey. And then when you needed more supplies, we headed to the mega metropolis of Termas del Flaco. This is the main street you can see here, bustling with commerce. This was our favorite hacienda and tienda, so we'd stay one night a week here, and you can't see it, but there's a bunch of grocery supplies in here, so we'd get our 6 days worth of groceries, get 3 square meals, go sit in the hot springs, and have a roof over our heads one night a week. And when we needed a major break from field work, and I did not plan it this way, but it turns out directly west, Chile is a really skinny country. Well, directly west from my field area out on the Pacific coast is Pichilemu, and for those of you who don't know, this is like one of the more famous surf spots in Chile. And so when we needed a good break about midway through the field season, we'd head out to Pichilemu, this beautiful black sand beach. But as far as I can tell, the sun never shines there, but the waves are pretty big and actually kind of intimidating. And apparently Captain Jack Sparrow lives there. All right. So anyway, back to business. Back to talking about mapping the Abanico Formation. So again, this is this photo I showed you earlier. And when I step back and look at this, right away I can see changes in colors and weathering characteristics. And when you get your boots on the ground and start looking at stratigraphic sequences, it turns out you can actually identify a pretty good mappable stratigraphy here. And lucky for me, it all worked out with the Geochronology, which was a real confidence booster. I should say I didn't actually get a lot of my helpful Geochronology data until I'd done all my mapping. So there was a few months there where I was stressing, like, am I gonna just have to quit because my mapping's all terrible, or are these ages gonna help me? So luckily it all worked out. Okay, so this is a highly simplified geologic map of my field area, and this is about 1 to 100,000 scale, or at least when I drafted this one. And so I'll briefly walk you through this, but kind of the main features you have here is this kind of northeast trending fault zone here. So to the northwest of that, you more or less have a homoclinal section of only Abanico Formation exposed at the surface, dipping off to the northwest, except for where locally folded. And then east of that, you only have the youngest levels of the Abanico Formation, so things younger than 36 MA exposed, and those are unconformably overlying older Mesozoic sediments. So that's kind of the gist. So I'm going to talk a little bit more detail about this. I can skip this slide. I basically did a whole lot of GIS work, and I made sure everything was up to the FGDC cartographic standard, but that probably doesn't mean much to most of you. Okay, so a little bit about the stratigraphy. So some of the common rock types, I'm not going to read these all off to you, but you basically had 3 main groups: volcanic, volcaniclastic, and epiclastic deposits. By and large, most of the Abanico Formation is made up of these volcanic and volcaniclastic deposits, so things like basaltic andesite lava flows, or basaltic to dacitic lava flows, ignimbrite or tuff deposits, block and ash flow deposits. The volcaniclastic units are what I interpret to be these lahar deposits and debris flow deposits. So let's take a look at each one of these real quick. This is typically what some of these volcanic deposits look like. So this is a really thick section, over 500 meters here. of volcanic flows and pretty much nothing else. So all these little squiggly lines you can see in here, those are all individual lava flows, ranging in what I would guess to be basaltic andesite to andesite in composition. These are some more stratified lava flows you can see here. I'd guess that these would probably be basaltic andesite in composition. And then this is a close-up of a ignimbrite or a welded tuff. All these little wispy things you can see here are flattened pumice, or what we call fiamme. So that's what some of the volcanics look like. This is what they look like in thin section, but we can skip that. Volcaniclastic deposits is what some of these look like. So on the left here, this is like a classic debris flow, or what I interpret to be a debris flow deposit. So you have these kind of coarser clasts in a matrix sand, or a muddy sand matrix. Here's a close-up of what I interpret to be a lahar deposit. These things are purple weathering, kind of tend to be finer grained but poorly sorted, kind of muddy sand up to granule size debris. But these are the fossil-bearing units in the higher part of the section. So this is a jaw you can see here. I'm not even going to pretend like I know what type of jaw or anything about it, but I'll take Andy's word for it. And this is a kind of a drawn back photo of some of these lahar deposits. In this case, they're dipping off to photo right, and they're this massive purple weathering, easily recognizable deposits. And then these are what some of the epiclastic deposits look like. And I didn't see a whole lot of these actually into the upper levels in the section late in the history of this region. And so volumetrically, they're not as significant as the other types of deposits, but they typically consist of these cross-bedded sands and gravels. Typically have these lenticular bed forms with erosive bases. Saw a lot of intrusions, and I basically mapped these as two units, although I will say we didn't have good age control on these. So, I mean, these things could maybe represent a whole slew of magmatic events. But nonetheless, to keep things simple, I just looked at their mineralogy and their textures and kind of broke them into two groups. So you had these mafic intrusions that were brown weathering. They had things like pyroxene and olivine in them. Then we had these more felsic intrusions that typically had a lot of hornblende in them. I'd guess they'd probably be dacitic in composition. As far as what these things looked like in the field, they had a whole range of sizes and geometries. So they could be very planar dikes or sills that were only a few meters wide to big blobby bodies that were hundreds of meters wide. Again, poor age control, but the few ages I did get suggest that maybe the diabase intrusions in general, and again, I'm not going to make any huge correlations here, but in general, the ages that we got seem to be 31 to 38 MA, whereas the more felsic intrusions are about 1.75 MA, but don't have a whole lot of data on that. Okay, so a little bit about the stratigraphy. There was basically two domains that I recognized, separated by this fault zone here. So we had this western domain and an eastern domain. So the western domain was basically all Abanico Formation, ranging from late Cretaceous to Miocene in age, whereas the eastern domain had at the surface only had the younger levels of the Abanico Formation exposed, and they were overlying the Mesozoic stratigraphy unconformably. So here's some very schematic stratigraphic columns representing each of these domains. Let's see. So again, the western domain is mostly just Abanico Formation capped unconformably by young quaternary volcanic deposits. As far as compositional trends, what I did notice is in the lower section of the Abanico Formation, we saw mainly primary volcanic deposits. As you move up section, we started to pick up a lot more volcaniclastic deposits. And then finally, at the top of the section, you get into some of those epiclastic deposits. And then the eastern domain, again, we only have the youngest levels of the Abanico Formation sitting right on the older Mesozoic stratigraphy. So this introduces a really interesting problem, right? So what happened to the lower Abanico Formation? So again, in the western domain, we have this lower 2.6 kilometers of Abanico Formation, and it's missing on this eastern domain. So what's going on here? Well, as with all things in geology, you can probably think of a whole slew of different options here, but I've kind of distilled it down to some end-member models here. One being the classical interpretation that people before me have made, where you had crustal extension during deposition of the Abanico Formation that resulted in a thick section of the Abanico rocks to the west, and no preservation, or not that much preservation of the Abanico Formation to the east. Alternative to this model is that you could have laid down the Abanico Formation first, and then faulted it afterwards, and which would have resulted in exhumation of the footwall block and erosion of the Abanico Formation. Another solution would be, you had this west-directed thrusting and a tectonic basin associated with that accommodated accumulations, thick accumulations of the Abanico Formation to the west and not to the east. And again, similarly, you could say, well, maybe you laid down the Abanico Formation first and then faulted it, eroding the Abanico Formation from the hanging wall. And then a third model would envision no tectonic basin, and that you simply just had a buttress unconformity. So maybe you had some broad, irregular surface that you were erupting these deposits upon, or accumulating these deposits upon, forming a buttress unconformity. Now, I guess I'm running out of time here. I don't want to go into the details, but right now I'm preferring this model, which is kind of a stark contrast to what people thought before me, and I have several lines of evidence for that. One being that I don't really see evidence for either extensional deformation or shortening deformation prior to accumulation, or any sort of evidence of this earlier shortening deformation or any extensional deformation. But this could be extensional deformation can be hard to recognize because it could be overprinted by later shortening that I do see. I also don't see any detritus that would be either come from the footwall or the hanging wall in the Abanico Formation, especially the older Mesozoic detritus, which would be really easy to identify. Okay, so that's the stratigraphy bit. Let's real quickly talk about the structure. There's basically two structural domains, a northern domain and a southern domain, delineated by this inferred tear fault underlying the Tinguiririca River Valley. So I'd like to show you a cross-section from each. Starting with the northern domain. So the northern domain was characterized by what I interpret to be fault propagation folding. So this is a geologic strip map and a schematic cross-section illustrating that. Where, let's see, and I collected some fold data, but I'll skip that for now due to time constraints here. The southern domain is characterized by this imbricate thrusting, and you don't really see a whole lot of map scale of folding south of that tear fault. So bringing these two cross sections together, this is kind of what I think you have going on. So you have this tear fault, which I'm trying to show with this semi-transparent white plane here. So that would be underlying the Tinguiririca River Valley. And so to the south of that, you'd have this imbricate thrusting of the Abanico Formation. To the north, you'd have fault propagation folding. Okay. I think I'm just going to skip this because we're running out of time here. But going on to the timing of deformation, we have a few things that, a few constraints on this, not super solid, but pretty good. First the first thing I should say is that a lot of the tight folding that we see is generally restricted to units of the Abanico Formation that are older than 37 MA. But then we see a lot of these undeformed mafic sills cross-cutting these larger deformational features. And I tried to date this particular one, but it was too altered. So I made some correlations, which is kind of going out on a limb here, but I dated similar intrusions nearby at about 38.4. So if we were to correlate those, that would suggest that shortening was well underway, or in this case, complete by 38.4 MA. Another line of evidence I have regarding the timing of deformation, or constraint on the timing of deformation, are what I interpret to be growth strata. So what you're looking at here is the contact between the older Mesozoic units and the Abanico Formation, which is darker colored here. And I'm showing the apparent dip with these balls and sticks here. And what you see is that you have this fanning of dips as you go from the older Mesozoic units all the way up into actually the Quaternary volcanics, which are basically flat lying. So if these indeed were growth strata that were accumulating as deformation, was happening and things were tilting and rotating, then that would suggest that the shortening was underway by at least 36 MA. I've dated the lower levels of, or the Abanico Formation along that contact there at 36. So, and maybe continued all the way through the Miocene, but was definitely complete by the Quaternary. Okay. And so bringing this all together for a simplified tectonic model. My model, so I'm revising previous models quite a bit here with my results, but it's still somewhat of a three-stage model. So I agree. I think the Principal Cordillera was in a back arc setting from the early Jurassic to late Cretaceous, and so that's when you accumulated those older Mesozoic units. And then during the late Cretaceous, and maybe even older, you had the onset of volcanism. And tentatively, or I'm going to interpret these deposits as intra-arc deposits. So that would suggest that the arc front had migrated from the coastal Cordillera to the Principal Cordillera by this time. And right now, all the evidence I have suggests that I don't really have any evidence that the Abanico Formation accumulated in a tectonic basin. So I'm going to go with this buttress unconformity model, which I'm sure is going to rattle some people's noggins, or I'll probably get some negative feedback from reviewers, but yeah, I'm going to go with that for now. And then I'd say by the late Eocene, shortening was underway, and you know, you had the shortening, deformation, imbricate thrusting, and fault propagation folding, and continued volcanism. So you're still accumulating arc strata while this is going on. Okay, so this is the figure I showed you earlier, and I'm basically just plopping my inferred results here, and it shows you that they're wildly different than other people's, especially, and I don't think anyone can really argue this, the timing of magmatism based on my geochronology results. I mean, you just can't argue that data. So, yeah, so it'd be interesting to see. I'd like to continue working north and south, but now that I'm in Montana, that might not happen, but maybe people in the future will do more careful studies similar to mine. Okay, and yeah, so the conclusions. You know, I'm greatly revising the chronostratigraphy for the Abanico Formation. It's at least 3.6 kilometers thick, probably thicker than that. It's dominated by volcanic and volcaniclastic deposits that I interpret to be deposited in an intra-arc setting. So this, you know, and as a consequence, that means the volcanic arc had migrated eastward by the late Cretaceous, and I'd argue that shortening was underway by the Eocene. And so that's the end, and I'll take questions now, and this is how I felt at the end of my PhD.